results, and that is actually the first time that I gave a talk here at IITP. It was online, so it was about this paper. I'm very happy to be here and talk to you in person. And so with simple operators, this time we look into the connection between LIGO and PTAs, and in particular, this is going to be the focus of this talk. We're going to assume that future experiments that probe the Hertz regime will be able to detect a merger event from subsolar primordial black holes. And then we will look into the associated effect in PTAs, as I will explain soon enough. But I will also mention in this talk a new research direction with Mr. Ivanov from MIT and PTAs, where we will use observations from last-scale structure, in particular Lyman-alpha forest, in order to constrain primordial black holes, which are not subsolar, but they are in the supermassive regime, same ones that we try to invoke for the seed of accelerated galaxy production for Jennifer. And so the first part of the talk will be dedicated to this connection between some solar PBHs, which would be an exciting new physics signal on their own. But would this new physics on subsolar PBHs also imply a new physics effect on PTAs? So the spoiler to that is that actually we do find a correlation and an overlap between the two regimes. And then I will talk about the Lyman-alpha forest briefly and its connection with supermassive black holes. And here the spoiler is that the Lyman-alpha bound is going to kill all of the supermassive regime up until the scale of the stupendously large black hole. So this is just a spoiler. I will give you the figure enlarged later on in the talk. So the outline is first I will talk about how primordial black holes are formed in the first place, and then how they can source gravitational waves where both LIGO type experiments and PTAs are going to be sensitive to. And finally, I'll talk about these Lyman-alpha constraints on the supermassive regime. So first of all, PBH is one of the most long-studied scenarios of new physics objects that are capable of leaving their imprint in cosmic history. They can span a large range of masses, from masses in the asteroid region. Here, this is the mass as a function of their fraction with respect to dark matter. And here you can see that there are no bounds in this asteroid mass region, and that is the region where it could actually account for full dark matter, so at F=1. So this is one of the most interesting regimes. But then also here, if you allow for a fermial abundance, you can have primordial black holes where just right after the LIGO discovery, they have been immediately identified as possible source. So these black holes could be of primordial origin. And there are also, for many years, the discussion of whether they can accrete to become the supermassive black holes that we know exist in the center of the galaxy. And then there's the supermassive regime, from then the 6 solar masses, then the 12. And finally, the slabs, the stupendously large black holes, which they cannot be dark matter, of course, they're too heavy for that, but they can just transverse the intergalactic medium. Now, excuse me for a little bit of technicalities, but I want to set the stage and formalism for the phenomena that I'm going to discuss. So we will start by assuming spherical symmetry. That's how we can perform our calculations. And we also choose the Komovian gauge, as it's the gauge that is being more useful for this type of calculation. And then we will define this quantity here, the expansion parameter epsilon, where this is the scaling factor, Hubble parameter and the co-moving length scale for a wavelength k. And we're going to work in the long wavelength approximation when this parameter is very small. And so if we are in this limit, the perturbations are super horizon, then we can assume that its paths evolve on its own as a separate universe. This is a separate universe hypothesis. And so locally it can be written with a parallel W type of metric. The only difference is that now the curvature is function of the microordinate R, and so it's varying. But I can also write it like this, and I can perform a coordinate transformation to connect the two. In this form here, you may notice that the implicit gauge is not a co-moving gauge. It's the uniform density gauge. However, up to order linear order in Z, one can solve that they're equivalent. So the calculation was first performed by Sokratis and Saki in the in a gauge similar to this one here, but then the one that people are using these days is the calculation by Bonar and Musco, where they are doing everything with the co-moving gauge. Then we're solving the Einstein equations, which are called Witten-Sharp-Hernandez equations in this context, and we obtain the density contrast as a function of transfer parameter, which is called 2/3 for radiation epoch, a co-moving scale, epsilon, and then this factor here, which is the curvature. And equivalently here, you see the same expression with respect to curvature zeta, scalar curvature zeta. And already from this point, you see that there is a highly nonlinear connection between the density contrast and the curvature perturbation. So even if you start with a Gaussian zeta, you unavoidably will get a non-Gaussianity introduced in my density contrast. So based on that, people have noticed that if you are to formulate a PBH formation criterion, you better not use zeta, but the density contrast, in particular the density contrast integrated over a volume of radius r, and this is called the perturbation amplitude. So it is an average quantity, and once I perform this integral, I can show that it is directly connected to the curvature. So in other words, this curvature K is measuring directly the mass excess within a volume V. Then we can talk about the time where these perturbations are re-entering the horizon. So my epsilon parameter is 1 in this case. And the peak amplitude is defined as this quantity here. And it is, one can show, again, by simple algebra, that it is connected to the density contrast. So this relation connects the amplitude, which is an average quantity, to a particular value of the density contrast at scale Rm. So this is the scale that we're interested in. And one can show that it is also the scale where the so-called compaction function is maximized. So compaction function is the main object that characterizes the PBH formation. And it is basically, you can already see here from the ratio that intuitively 2gm equal r, you have the formation of horizon. So again, this is the main object, which is related to the compaction function, and this is the object that we're going to use for the formation of our criterion, for the formulation of our criterion, which is this one here. So the density contrast has to be above a certain threshold line. Before explaining to you the dependence of the threshold value, I'm going to assume that there is an inflation scenario, inflation setting, which produces a curvature power spectrum. So I can define here the following equation. This will be my power spectrum, and this is the point for later. And I will remain agnostic with respect to the dynamics of inflation that will cause the creation of the power spectrum. So I just saw your email that maybe when you actually include inflation, there can be important consequences about what is allowed and what is not allowed with respect to this discussion. But for the time being, so I'm very curious to discuss this after the talk, but for the time being, I'm going to be on a phenomenological level. I'm going to start by the assumption of a log normal power spectrum, which is kind of generic. And this will be my starting point, basically, for what zeta is. I'm not going to talk about what this results from inflation. And now, once we have this power spectrum, coverage power spectrum, we can formulate the PBH formation criterion. And as we see, this is a high nonlinear effect, a rare effect. So the formation comes from the Taylor distribution, and the criterion is satisfied when there are peaks of this quantity delta n. And on the top of that, these people here found the dependence of they have a simple prescription for calculating the dependence of the threshold value on the shape of the power spectrum. So you see here, this is the y-axis is the threshold versus the delta, which is the width of the power spectrum. Next, we'll talk about the distribution of masses of these primordial black holes. So the mass results from it has been numerically certified. It follows a scaling law. So it is a function of my peak amplitude, and it is related to dimensional parameters, which, by the way, are again depending on the period of the formation, because when we're close to QCD phase transition, they are also functions of the temperature, and also to the horizon mass at the time of formation. So intuitively, the resulting PBH is it's very close to the mass of the horizon. Of course, it's not only one mode that contributes. There are more than one mode that contributes, and the whole process happens in real space. So it's not exactly the same as the horizon mass, but to a good approximation, this is the relation. And then we can also connect the horizon mass to this scale Rn. So it will be a function of the scale where I have a big amplitude. And then, so I already mentioned we want to investigate PBH formation over a wide range of scales. So we introduce a smoothing function W, which is going to be the top hat. Like, this is rewriting the same definition for the average density contrast here, but introducing the top hat window function in real space. And then we can move into the Fourier domain, and my top hat function is going to become this W tilde here. And I'm also introducing a linear transfer function. Yeah, this also has a quite complicated form. And now I am equipped to translate the power spectrum from zeta to the power spectrum on this linear quantity here, the delta. And I will perform the integral in order to do that. And this is the expression for the variance of my delta. Delta L here is equal to delta M when I keep only linear terms in zeta, by the way. And finally, I'm going to use press-sector theory. So it's going to be a calculation based on the press-sector formalism. Notably, there is another way to calculate this phenomenon, which is a theory of peaks. The caveat of our analysis is that there is a discrepancy between the two methods, and we are focusing on per sector. This is because non-Gaussianities, which are going to be important, are not so well understood in the theory of peaks framework, and they are also there are some studies that show that if the theory of peaks is describing the effect, then probably there's no real connection between the subsolar regime. So keep that in mind. But for now, we're gonna go with per sector, and in that context, the PBH distribution of PBH masses, the mass function, can be written in the following way. And okay, this is a rather complicated expression, but in the end of the day, it's the same procedure that we're doing when we're calculating the galaxy clustering, for example. What it is to be, the message from here is that my mass function is going to depend on this Gaussian distribution here, and here in the denominator I have of my exponential, I have the variance, which is connected to the amplitude of my primordial power spectrum. So there is a very, very sensitive relation between the mass function and the amplitude. So you change the amplitude a little bit, you're going to have a much different mass function distribution. As we will see later, the gravitational wave power spectrum is much less sensitive to the amplitude. So it goes as say to the fourth. So there, this means that I can basically still produce gravitational waves even if my PBH abundance is very low. So next, yeah, these are two examples of my PBH function, mass function as a function of mass, for different choices of the width here, and for different choices of this non-linear, non-Gaussian factor. So we're going to, we already talked that due to this nonlinear relation, we already expect non-Gaussianities to appear, but you can also start from the primordial power spectrum with non-Gaussian scalar curvature. So we will parameterize as usual with the power series, then got non-Gaussianities with these quantities here, and they are enough for the description of the phenomenon. So we can truncate at higher orders. And then again, in these papers, one can find prescription to incorporate these effects into your mass function calculations. And as you can see here, the effect is quite important. So with negative non-Gaussianities, you can pump up the power the mass function a lot. And yeah, finally, I also want to notice that from now on, I will use the following average quantities for the mass structure, for the fraction with respect to dark matter, and for the PBH mass. So I'm going to translate these extended distributions into monochromatic primordial black holes in order to match with phenomenology. So this is a good approximation. And whenever I talk about PBH relation, I'm going to basically refer to the average quantities.
Sorry. Why do you have a suppression for positive non-Gaussianity? Usually we expect
intuitively, the non-Gaussian part is spreading.
Okay.
So I'm increasing the tails of the distribution. So
when FNL is positive, the tail is enhanced, right? It's similar to the Skurnik.
I think there is a relative sign, which is the important thing. I think it's a matter of definition here. So the gravitational waves is insensitive to the sign because the FNL enters with a square, but here it's actually the sign is important, and I think there's a relative sign. So this definition with a negative FNL is the one that is going to create the spreading and increase the tail. But we have to look at the exact definitions to see that. I have to look at the exact formulas to find this concrete point.
So how you get this last formula? Not quite obvious to me. The last formula. Yeah. Yes.
This is just defining the average of my quantity. So this is the average of the function.
Yes.
And this is the average position of my mass function. So these are standard law of how to translate these extended functions to monochromatic ones. It's just a statistical definition of the average quantity in this context. Yeah. Okay. So this is what I'm equipped with, and now I'm going to talk about the gravitational wave. And yeah. So first, this is a general picture. As we already noticed here in the Hertz kilohertz regime, we have LIGO Karga experiments already taking data, and there are also future suggestions, proposals. Then there is this crazy proposals of putting lasers in space, which is LISA, and will extend the range down to these frequencies, and finally at even lower frequencies, millihertz here at nano-Hz, we have the pulsar timing arrays. And this is standard catalog of events. There are 90 merger events already at the third run of LBK. Okay, these are some observables. This is not so important for us. What is going to be important is the fact that usually the masses of the two merging black holes are the same order of magnitude. And yeah, there is also one candidate event from the last run, which is not exactly, it's on the cusp of gravitational wave detection, and it features subsolar masses. So, well, people in the Physics Institute have noticed this, and they have studied the possibility that it's actually subsolar PBH, which is merging. They also conclude that the associated effect, the PTAs that we're going to talk about, is too large, but they start the Gaussian gates. So maybe with non-Gaussianity, this result is altered. But in general, a subsolar discovery would be a smoking gun signature for new physics, because there are no known astrophysical production channels for such black holes. And so this is the timeline here. We are going to have all four this year. So we're very excited about this. And then all five will begin in 2028. And there are already quite a few papers in the literature in the last couple of months, if you notice, that talk about subsolar masses. Here's the abstract. Or I think this number is wrong. It's from last a few months here. So you can look up with the title. But the authors notice that if you assume events with the same threshold as the candidates from all three, then all four projected sensitivities would allow ruling out the presence of neutron star tidal forces at 3 sigma, which only leaves primordial black holes as the possibility. So this can strengthen the PBH hypothesis, and future experiments will lead to even stronger conclusions. So this is an exciting time to think about the subsolar regime. Talking about gravitational waves, I'm going to talk about binary formation. So following their formation, the PBHs themselves, they are sparsely distributed. I'm going to approximate them as a so-called Poissonian gas, and we're going to assume no initial clustering. And well, initial clustering makes the situation more complicated because on the one hand, you have well, clustering increasing the merger rate, but at the same time, it also increases the presence of other binaries, other black holes that can disrupt the binary system. So it's not clear what exactly happens with initial clustering at the moment. But then, soon enough, even if their initial distance is big, the Hubble flow overtakes it, and they come closer, and they decouple from the expansion rate when they are becoming gravitationally bound. So when their energy density exceeds that of the background. And this leads into the so-called early binary formation channel. And if there were just two PBHs that would just cross into each other in the presence of a third one, which provides the necessary angular momentum, they create a binary pair. And they can be evolving isolated until today. In that case, the only energy loss is via these gravitational waves. But they can also enter clusters of other PBHs, and then there are mechanisms where the binary can be disrupted, as we will see next. There's also this path here, the late binary formation, where we have isolated PBHs that later on meet when they are inside halos, and when the halos themselves meet. However, this is a much more rare phenomenon, such as bleeding, and we're going to disregard it. So this whole process is captured by the merger rate function, which gives you a time t when the binaries form. And when we neglect accretion effects and initial clustering, it gives you the merger rate. And it is treated to numerical simulations from GR. However, it depends on this suppression factor here, which can be formed or split into two components, the early and the late one. And the early component encodes the disruption of binaries when you have two PBHs, and the third one passes by, disrupts the binary in the radiation epoch. But also later on in the late universe, you can have a similar effect when they are the PBHs are absorbed by clusters. And so here you see a plot of the suppression factors as a function of the FPBH. And this is the combined effect. So for rare enough PBHs, it scales as 21/37 of FPBH. Again, this comes from the latest time effect, especially comes from numerical simulations. And here's the plot of the combined merger rate as a function of PBHs as well, for different type of benchmarks for the PBH mass. Then the binary enters three phases of evolution. First, we have this inspiral phase, where the binary they orbit around each other and gradually they lose their energy. This is by far the phase which lasts the longest. Then we have the merger phase, where it marks the point of the black holes come into contact and they begin to overlap. And they generate a burst of intense gravitational waves. And finally, they settle down during the so-called ring down phase here, and they basically become a single object. And so again, we have templates, numerical templates, where we feed our gravitational wave signals. And how do we detect the signal? We define the so-called signal to noise ratio, which is these empirical fits on the gravitational waveforms, which is here, this H tilde, the numerator, is the amplitude strain in Fourier domain, over, again, templates of the noise bar spectrum, which comes from the gravitational wave detector. So its detector gives you its own SN function. And this is the SNR will be a function of the mass of the PBHs and the emerging redshift. So here on the left side, we plot the strain in Fourier space for 3 different PBH benchmarks again. And you see there are not a lot of differences except for the frequency of the return, which is lower as you go down in mass. And the redshift is chosen so that we have an SNR of 8 in our detectors. We take here the Einstein telescope for this plot. And then we can also plot. We're going to have a contour plot of my SNR in the redshift versus mass domain, and the blue line here is the Einstein telescope, the future experiment. The red one is the LIGO 05 run. So you see here the cover of Einstein telescope would be even lower masses for the benchmark 8 and for also higher SNRs. So now we can calculate the number of detected events. It will be a function of this, not directly of SNR, but of a probability distribution with X SNR as an argument, and it accounts for the fact that we have a random orientation between the detector and the PBH binary. So this integrates over all these various choices for the detector alignment. And then we also have to integrate it over the redshifts. This is a convoluted volume term. This is the merger rate that I presented before. And there is also one more factor, which is it's called the local density boost factor. And it takes into account that in galaxies like the Milky Way, where you have an over-dense region, you have a higher probability of encountering binary systems, and everything is multiplied by the observation period. So for 5 years of observation period, and for setting 3 events as my detection threshold, I can now plot in the PBH parameter space at the reach of this future experiment. So this is spanning here from 10⁻² solar masses to 10 solar masses. And this will be the 04 run. It will give me this subsolar part, which is not excluded by Eros and Ogle, which are microlensing experiments. And in the future, Einstein telescope is commissioned, and with the Cosmic Explorer, we will be able to probe all of these Brazilian down 10⁻² solar masses. So exciting years ahead for gravitational wave astronomy.
So what's new to do in this plot to get this constraint compared to the previous constraint for the subsolar mass primordial black hole?
There is one more calculation of this type that we agree with and we produce by these people here. So, but yeah, I'll show you how this plot, when we enter the scalar-induced gravitational waves, how they enter this plot. So we can have both things together, and we can see if there's any overlap. So let's go now to PTAs. So yeah, as already noticed, these collaborations, they release evidence for the existence of this stochastic gravitational wave background. 67 pulsars so far in 15 years of observation. And this is a famous plot, all seen that helps down angular correlation, which is prediction of GR. And as you can see here, the data points align with it. So yeah, probably I don't need to explain the what is happening here and what is the mechanism. All familiar with PTAs. And we also have a standard astrophysical explanation, which is in terms of the supermassive black holes that already exist in galaxies. But it is known already from the physics paper of nano-Hz that there are various new physics models that can actually enhance the fit. They can produce better fit. There are like only 3 candidates, I think, that are still valid. First order phase transition, large gravitational perturbations, and domain walls. Not so severely restricted by other phenom. We're going to focus on the large gravitational perturbation in this talk. And again, a little bit of formalism. We start with a Newtonian gauge. Here, this is first order in the Newtonian potentials phi and psi, and second order in my tensor Hij. And the same curvature perturbations that collapse from PBHs are also sourcing gravitational waves at second order in perturbation theory. So this is the equation that I can write out schematically here. T is the projection operator, and S is the source function that depends on the derivatives of my scalar perturbation squared. And that's why it is a second order effect. And I can also define my power spectrum for the tensor fluctuations. And I'm using, again, a transformation in the Fourier domain for my tensor. I'm writing down as components of these vectors here, epsilon, which are chosen so that they are traceless and transverse to the direction of the gravitational wave of the moment k. And emission takes place usually near to the hyperbolic crossing time. And then I can define my gravitational wave power spectrum. So this is going to be a stochastic event, in contrast to the LIGO type of gravitational waves, which are transients. Here, gravitational waves come from everywhere, and this is how I will define the power spectrum. It is going to be an average over polarizations of my my delta, my tensor power spectrum. And the Gaussian piece here, I can approximate it as the following function, and as already noticed here, the dependence on the amplitude, which is the power of the amplitude, as opposed to the exponential, which we encountered in the mass function. So then we have to go beyond the Gaussian piece and introduce non-Gaussianities again. This is the general definitions. This is a kernel function here, which encodes the source term and also the scalar mode green functions. And this time average in radiation domination. And here the non-Gaussian power spectra are again the result from an expansion where I am convoluting the Gaussian pieces, and I introduce the non-linear, the non-Gaussian parameters FNL and TNL, the same ones that we saw before for the PBH formation. And this is the picture that I get for 3 different choices of my primordial curvature power spectrum parameters that will land me into the subsolar regime, actually, together with the data from nanograph, this violin plots. And then I also have the irreducible piece from the supermassive black holes, which again can be given by this blue tilted power law. This is the usual parameterization. And then I can perform an analysis with 2 assumptions. First, that is just yes. Okay. The scalar-induced gravitational waves, but also scalar-induced gravitational waves together with astrophysical background. And this is our preliminary results. So here on the bottom is the same plot that you saw before, but now the blue line here is the 1 sigma contour fit from scalar-induced gravitational waves. And this is for the Gaussian case, and this is for the non-Gaussian case. And as you can see here, we do require this negative non-Gaussianities to go and slightly reach the subsolar regime, but not really there. I would say that unless we're in the highly non-Gaussian case, which cannot be treated by perturbation theory, there is these bounds from microlensing that would exclude an overlap between the subsolar PBH discovery and the scalar-induced gravitational waves press fit. And the same information here appears in the parameter space of my primordial parameters, the amplitude of the log normal, and this is the pivot scale, K star. And again, above this gray region here, we have overproduction of PBHs, and these are all the various future experiments. And this is the 1, 2, and 3 sigma cone towers for the PTAs specific point. So what happens when I include astrophysical background? And yeah, we're actually quite intrigued by this one. In this case, we see that we can basically cover the subsolar regime pretty well. So the combined explanation of scalar-induced gravitational waves and supermassive black holes, this is our conclusion at the moment, is consistent with a potential subsolar discovery. Or if you have a subsolar discovery, then the subsolar PBHs are due to curvature fluctuations. You expect to see a new physics result in your PTAs experiments. But you need also a contribution from the supermassive black hole background, which again is expected to be there. And again, the non-Gaussian case brings you to much lower abundances, and here you can have this overlap at 2 sigma, where in the Gaussian case we need the 3 sigma. So this is the main result of this work, and we expect to have it soon in the archive. So the final verdict on PTAs, this will be given when you have more pulsar. So future increase of observation time will increase the number of detected sources, so we need to wait longer. And there are some observations. So if you see spectral fluctuation, then it's mostly coming from this supermassive black hole. The BSM models do not produce such effects. And if you see individual supermassive banners nearby, and you can resolve them, and you see a deviation from the f to the minus 2/3 slope, then the first thing you will do is to infer something about the surrounding background, which is probably the dark matter distribution. And then there's this really great complementarity plot from Alice et al. Right after the PTA discovery, where you can see that in all the BSM models, there is no associated effect at LISA, but only the supermassive black holes lie here. We're gonna probably repeat this plot in the assumption of, in this scenario, of supermassive black holes together with scalar-induced gravitational waves, and see if there's any difference in this one. But yeah, in future, hopefully with this complementarity of experiments, that's the important point also when thinking about subsolar PBHs, that we might be able to have a verdict on what is exactly the source of PDAs. Okay, and I'll go briefly through this part because I think we're slightly over time. But yeah, I'm going to talk to you about these Lyman-alpha constraints. How much time do we still have?
Oh, we have no limitation.
No
for that.
limitation. Okay,
Yeah.
good. Okay, then okay. But anyway, I don't have a lot of details on this part. I just want to point out that large-scale structure is also going to be very important in the near future for constraining BSM scenario. So this is a plot of this future high redshift observations. This is the Lyman-alpha, and then at slightly larger redshifts, you have the ultraviolet luminosity function that I talked to you about in my previous talk here. And then in the future, we also expect the 21 centimeter astronomy. And the LSS is emerging as an observational probe, and the scales are as down as 1 versus megaparsec. We have a lot of future observations, but let us focus here on the Lyman-alpha forest, which arises from the transition from n equal to the n equal 1 electron transition in the neutral hydrogen atom. It corresponds to a wavelength of 1,200 angstrom, and it is observed that the rate of redshifts, due to the multiple absorptions inside these clouds of intergalactic gas. So it's a main tracer of the intergalactic medium. Maybe I can also play here this plot. So as you can see, it was first observed in the 70s, and it was soon realized that it is it's not due to some physical interaction, but it is within the spatras themselves, but it is due to this absorption inside the clouds. So each individual cloud leaves an imprint on the absorption line at different positions, and we can use this data. The physics of this process is quite well understood.
So this is simulation demonstration.
This is the data, just the data.
Data. Okay.
Speaking of simulations, there are simulations, but here I will advocate an effective field theory approach developed here by Misha, and compared to simulations, it is a much it's a much cheaper and faster way to prove BSM. Simulations are resource intense. There are some emulators on the market, but it is hard to extend them for BSM type of studies. Here, simulations are excellent for you're not limited by range, whereas always in perturbation theory, you have to take advantage of the scale difference. So you can start with n bodies at very, very small scales. But since we don't have a first principle of galaxy formation, it is actually hard to encode the galaxy formation process. Instead, this is something that can be captured by EFT. And EFT works, again, by this magic of the separation of scales. So even if the galaxy dynamics are complicated, similar to how, for example, molecular dynamics are complicated in water, we can define these coarse-grained microfields. In case of water, you have density, you have velocity, and you can derive those higher-order terms like viscosity. Similarly, in the case of galaxies, you take advantage of in the water, you have an expansion parameter, which is the mean free path for the motion of the molecules. In galaxies, you have basically relevant for Lyman-alpha. You have the scale around 5 inverse megaparsec, where you are expecting non-linearity to enter. So you are in a halo size, and then you have at even lower scales the Jeans length, where the gas perturbations are smoothed out by the pressure the gas. And so you can you can use this as an expansion parameter, and you can write down the galaxy dark matter connection. This is the energy density real space of my galaxy, and these are terms. This is much longer expansion. I'm just keeping here the linear term in the dark matter energy density and the quadratic term, and also this term is the velocity, a normalized velocity. And here I'm adding Newton's parameter, which I'm going to fit over in order to be able to capture all the nonlinear effects in aggregate. So this is a match with simulations and data, and you can see here that the AFT works quite well. I fortunately don't have much time to go into details. Just want to mention that for the high redshifts and low scales that we're interested, there are data available by Harris and Mike surveys, and there we are in between the linear and the regime where the unit scale enters and unit is and both simulations. In the semi-nonlinear regime, you have terms that are quadratic and the fourth power of k, where k here is the wave vector projection along the line of sight, and they're captured quite well from the EFT. So I can map these coefficients here for the one-dimensional power spectra of my Lyman-alpha to the Newton parameters of my EFT, and yeah, there's a very good description. Up to some reionization effects which are not yet captured by the EFT, but are existing simulations like the one from Muji et al., which is taking that into account. And then on the other hand, the PBHs themselves, they follow the adiabatic perturbations on large scales, but on small enough scales, we have their discrete nature that enters, and it generates an isocurvature component. So you have a Poissonian gas, the isocurvature component is the variance of my density field of the PBHs, which is inversely proportional to the number density of my PBHs. And then one can simply modify the matter power spectrum by adding this isocurvature piece and trust linear theory up to this cutoff scale, which is the scale of non-linearities that we saw before. And this is how it looks. You have this pump here for a particular population of supermassive PBHs, which is going to be constrained by all the Lyman-alpha and the UVLF data that lie into this regime here. And last year, I showed you the UVLF constraints on the parameter space, which are this blue line here. But this year, I'm coming with a Lyman-alpha constraint, which, as I already gave you that in the beginning, it is basically excluding all the parameter space up to FPBH of 10⁻�3. Beyond that, linear theory breaks down, so we cannot trust the previous picture about PBHs Poissonian gas. We have very, very rare PBHs that evolve with a so-called seed effect. But above that, yes, this Lyman-alpha is going to be the strongest constraint for PBHs and everything else that can do this modification to the power spectrum. So it's good to know there are no subs around flying in space. Yeah, and that is all. Thank you very much for your attention.
Sorry,
Yeah.
So this constraint depends on the statistics, like the Gaussianity and other. Usually you assume a Gaussian distribution.
You mean if this is altered, let's say with some initials?
Yeah, similar to this wave dispersion constraint, which depends on the Gaussian distribution for curvature dispersion. Do you have this Lyman-alpha constraints, which is so strong? Then how about the non-Gaussianity?
Yes, this is true. That I am assuming this simple modification of the power spectrum here, and I'm not capturing the initial clustering, let's say, of PBHs. However, if you're close to PBH equal 1, you already have the Gaussian piece contributing, right? So you would expect the Poisson effect itself to be present, and that would be captured by Lyman-alpha. Now, if you have some extreme non-Gaussianities, maybe they are more important, I would say, as you go down in FPBH. So that's still open, but I don't know anyone that has calculated that in the literature yet. It would be interesting to, but it would require simulations for sure.
Okay, so this isocurvature provision you introduce is a kind of a consequence for the existence of primordial plateau.
If they are not initially, well, yeah, in the limit where they are just Poisson distributed in the beginning of the formation.
And how about this cutoff?
The cutoff is the cutoff you mean in the non-linearities here.
Yeah, it seems that this cutoff.
We vary that as well. So we vary that as well in the so basically in this Lyman-alpha EFT, you can add everything in Monte Python, and you can add this nonlinear piece, and you can vary the cutoff as well. So this is another parameter you can run your Monte Carlo over. And what I'm reporting here is with variation of the cutoff.
Yeah, so you have a kind of a lower bound, so it is around 10 to the 5th solar mass or something.
Yes, exactly.
So is that depend on the? Does that depend on this cutoff?
Actually, yes. I think that you can no longer when the PBHs are even lighter.
You mean that it's not trusted in some sense?
I think that okay. What happens here is that you cannot even probe these scales with Lyman-alpha anymore. So they are at the level where you are at scales much closer to the inside the halo. That yeah, you can only use all of this linear theory basically.
Okay.
Okay. Any other questions for either one of these two phenomena?
The one comment is this non-Gaussian thing. So in your final result of this preliminary thing about this combination of LIGO results and
Yeah.
From here it's can I go one slide before? Yeah, if you look at this lower two panels, it is obvious that if you introduce a negative non-Gaussianity, then the amplitude you need is larger in some sense, right?
So if I introduce the non-Gaussianity,
Yeah,
I can produce with lower amplitude more PBHs.
Yeah. So this means that if f(n)L is negative, then for the same amplitude of the curvature perturbation, the PBH abundance is lower.
Yeah. Oh, isn't that the inverse? Wait. If you for negative non-Gaussianities,
and you fix the A of zeta.
Okay, so let's say I'm here in this line. Yes.
Yeah, you fix it, then the amplitude of the PBH is lower. So
well, I fix the amplitude.
Yeah.
So, yes.
If you fix it, I mean, these figures are okay, but the one I asked the question is previous one, so it seems that the result is opposite.
You mean in this one here?
In
the beginning.
Slides before.
Yeah. This one. Oops.
I think that may be a typo.
Yeah, I guess it's.
You mean this one here?
Yeah, this one. Because it's
so this is fixed, and I am producing more. I'm saying here I'm producing higher FPBH basically.
Yeah, but that should be a positive f(n)L because f(n)L describes the skewness. It's just makes the tail heavier. Is that?
So with positive f(n)L, I am producing more PBHs
Yeah.
essentially.
Yeah.
So okay, let's see here. You might be right, actually. This is again a draft state, so maybe that is a typo.
I think the paper is okay, but
yeah, okay. Let's trust this plot more.
yeah, this is trustable, but the one.
But I intuitively, yes, I think that it increases the tails if you have positive FNL. That makes sense. I was confused because, yeah,
because zeta in some sense it has the same signature with the density fluctuation. So zeta is larger means that it's heavier. So you have the heavy tail, then you have more PBH.
Yes. I think you're right. Probably this is. Yes.
In your consideration, the PBH distribution for the boson distribution. But would that be possible? The PBH distribution deviated from boson distribution by the interaction or gravitational interaction from other.
So how does the Poissonian distribution is resulting? You mean during PBH formation? That is the question.
Yeah.
Or we can predict it if it is a different distribution from the gravitational wave. If there's a deviation from Gaussianity, you would have to talk about inflation, right? So you have to really.
I know it's a reasonable assumption that when the PBH formation, it should follow the Poisson distribution. But my question is, in following evolution, would that be different?
You mean after formation? Yeah, after formation you have clustering. After formation you definitely have clustering, but that's already captured by the Poisson effect. So that's the same way you treat the phenomenon the same way that you treat galaxy formation. It's later evolution. So that is taken into account. Can I ask you if these results are not agreeing with your paper from 2019 or what were the assumptions?
Well, I think it's irrelevant because in that paper, I have to assume that the perturbation to form primordial black holes will come from the curvature perturbation from inflation. But if you have other mechanism to generate these perturbations after inflation, then that constraint should not be applied. No.
But how I would get normal, but not from inflation, basically.
Yeah. So, but in this problem, you don't have to make such assumption, right?
Okay, but then what this is still important to note is that the log normals should not come from inflationary dynamics, which is but it's not so clear to me what is the famous model to do that.
Famous model to do that. I'm not familiar with.
Talking about the shape of the power spectrum or something.
Yeah, so how can I start with log normal but not for inflation? Because
that is okay. That's the simplest two-parameter model. If you want to go beyond, then yeah, of course you can construct more complex model, like the one of this so-called broken power law. That's the next one you should consider, and maybe.
No, but the point here is that the simple model is excluded, right? That's what you claim in your paper.
Yeah, I think we should discuss this. Yeah.
Good. Yeah, this is we're gonna see, like, even if O5 doesn't give us anything, I think this is a nice
sorry.
For future experiments. What's the reason?
I may have a problem to interpret this result. Are you ruling out this subsolar mass from a black hole?
I'm ruling out if it's just the scalar-induced gravitational waves. I'm not ruling it. I'm not ruling out the subsolar. Yeah, essentially, if there is a subsolar, then without supermassive black holes. I should see a scalar-induced gravitational wave signal. If I don't see it, then it means the subsolar PBHs are from some other mechanism.
I see.
But if I do see them, and then I am also taking into account supermassive black holes, then I expect that I can fit my PTAs. So I have I have an associated effect there. Now you can say that if you have subsolar discovery, is this a proof? This is like a no-go theorem that the PTAs is due to the scalar-induced. Well, it could be that subsolar is from some other mechanism as well, and then this would also be lifted. So we are already in the assumption that this is the common mechanism. Let's say.
Yeah, there are some candidates for the subsolar mass events in LIGO, right?
Yeah, I mentioned that already here.
Yeah,
I think also a paper from your group. This SSM 2003. Oh wait, right?
yeah, I think that's claimed by Sebastian and the other. So this is too large.
Well, here in this paper, one they find that
That's single group. Okay.
yeah, they find that the associated effect, which we also calculate, is too large. So you have too much of gravitational waves in PTAs.
No, that's okay. You can always
add the non-Gaussianities.
You can always add the non-Gaussianity.
Exactly. So these people here, they study tidal forces. They calculate log numbers for similar effects to SSM.
Wow.
And they say that if there is a similar effect, then with O5, they are going to know for sure about 3 sigma that this black hole is a neutron star. So yeah, we are all hoping for such events because it's going to be exciting. It's going to be really exciting for all type of BSM enthusiasts.
Sure.